The spacecrafts were flying at about 55 kilometers over the surface, and they were able to return the best gravity map ever of any celestial body.
For as long as humans have looked skyward, the moon has been both a familiar companion. From ancient myths that saw it as a divine being to modern conspiracy theories that cast it as a site of hidden alien activity, our celestial neighbor has never ceased to provoke wonder and speculation. Yet behind the sensational claims lies a far more compelling story.
The moon was heavily fractured in the exterior. Now, we knew from the bombardment in the early solar system that fracturing of the outside of planets has occurred. This is something that we call the planetary regolith.
No, this is not a myth or a legend. It is very well seated in hard science, patient exploration, and revolutionary discoveries. A NASA insider has just revealed that weird things are happening on the moon right now. So, what is the truth behind all of this speculation? Today, we'll answer all of this. The Grail mission and gravitational mapping. In September 2011, NASA launched the Gravity Recovery and Interior Laboratory, better known as the Grail mission, aboard a Delta II rocket from Cape Canaveral Air Force Station in Florida. The spacecraft were named Ebb and Flow by schoolchildren through a nationwide contest, and they entered lunar orbit around New Year's Day, 2012. Unlike other lunar missions that focused on surface exploration or sampling, Grail was designed to probe the moon's hidden interior by mapping its gravitational field with unprecedented precision. The two nearly identical spacecraft flew in tandem, maintaining a controlled formation while measuring minute changes in the distance between them caused by subtle variations in the moon's gravity. These changes, on the scale of microns, provided scientists with a way to see beneath the lunar crust and examine density differences in the subsurface that no camera or lander could reveal. The mission lasted until December 2012, when both spacecraft were deliberately crashed into a mountain near the lunar North Pole after depleting their fuel reserves. Despite operating for less than a year, Grail revealed paradigm-shifting insights. The spacecraft collected some of the most detailed gravitational data ever obtained for any celestial body. Its measurements were about 100 times more precise than those made by previous missions such as Lunar Prospector in the late 1990s. The dataset offered a complete gravity map of the moon, resolving features as small as 20 kilometers across, which represented a dramatic improvement over earlier maps that could only detect features larger than 100 kilometers. One of the major scientific results from Grail was the confirmation that the moon's crust is thinner than previously thought. Earlier models had suggested crustal thicknesses of up to 60 kilometers, but Grail's data showed that in many regions, the crust is closer to 34 to 43 kilometers thick. This finding had profound implications for theories of lunar origin, particularly the widely accepted giant impact hypothesis, which proposes that the moon formed from debris generated when a Mars-sized body struck the early Earth about 4.5 billion years ago. A thinner crust implied that the moon's early history of magma ocean crystallization and differentiation was more complex than we thought. Grail's gravity maps also revealed a surprising level of structural asymmetry between the lunar near side and far side. The side facing Earth, known for its dark basaltic plains called Maria, showed evidence of large gravitational anomalies linked to ancient volcanic activity and concentrations of heat-producing radioactive elements in the mantle. By contrast, the far side, which lacks extensive Maria and remains heavily cratered, displayed a more uniform but rugged gravitational landscape. This asymmetry helped explain why volcanic eruptions were far more common on the near side, while the far side remained geologically quiet. The research team analyzing these findings included scientists from multiple institutions, with Ryan Park of NASA's Jet Propulsion Laboratory in California playing a central role in refining the interpretation Grail gravity data. By applying sophisticated models of tidal deformation and mantle dynamics, Park and his colleagues demonstrated that the near-side mantle is more deformable under Earth's gravitational pull than the far-side mantle. This confirmed that the two hemispheres of the Moon are not only geologically distinct on the surface, but also fundamentally different deep inside. The likely cause was an uneven distribution of radioactive isotopes such as thorium and potassium, which continue to produce residual heat billions of years after the Moon's formation. Another important contribution of Grail was its ability to trace the origins of lunar basins and impact structures. The mission revealed that many large basins, including the Imbrium and Orientale, have ringed structures extending deeper into the crust than previously realized. These gravity signatures suggested that the Moon's crust and mantle responded elastically to colossal impacts, and that these events shaped the Moon's geological evolution more profoundly than surface imaging alone could show. The findings also provided a valuable comparative framework for studying impact processes on other planets and moons in the solar system. The precision of the gravitational field data from Grail has continued to serve practical purposes for modern lunar exploration. High-resolution maps improve navigation and orbit determination for spacecraft, ensuring that future missions, such as NASA's Artemis program and international lunar landers, can achieve greater landing accuracy. They also assist in identifying regions with resource potential, such as areas where concentrations of titanium or thorium may be more abundant. But that's not all. In fact, we're only getting started. The Moon is not what we thought at all. Discovery of lunar flexing. For long, it was assumed that the Moon was shaped primarily by ancient impacts and volcanism billions of years ago. Yet recent analyses of lunar data, especially from NASA's Grail mission, have revealed that the Moon is still undergoing a subtle but measurable process known as tidal deformation. This phenomenon is caused by Earth's gravity, which exerts a constant pull on the Moon. Although the deformation is extremely small, on the order of tens of centimeters, it provides valuable clues about the interior structure of our nearest celestial neighbor. The concept of tidal deformation is familiar on Earth, where the gravitational pull of the Moon generates ocean tides that rise and fall twice daily. In the case of the Moon itself, Earth acts as the primary tidal driver. The gravitational interaction stretches the Moon slightly, producing a bulge aligned roughly toward Earth. While this effect might appear negligible to the naked eye, spacecraft equipped with high-precision instruments have shown that the deformation leaves a measurable imprint on the Moon's gravitational field. Using Grail's data, Ryan Park of NASA's Jet Propulsion Laboratory and his team found that the near side is noticeably more deformable than the far side. This was not a trivial discovery because it suggested that the two hemispheres of the Moon, already visibly different in their surface appearance, are also distinct deep within their interiors. The near side, marked by vast dark plains of basalt known as Maria, responded more elastically to Earth's gravitational pull, while the far side, dominated by highlands and impact basins, appeared stiffer and less flexible. The difference in flexing can be explained by variations in the internal composition of the lunar mantle. Geological evidence and chemical mapping, including data from NASA's Lunar Prospector mission of 1998 and later orbital studies, had already shown that the near-side crust contains higher concentrations of radioactive elements such as potassium, thorium, and uranium, collectively referred to as KREEP, as in potassium, rare earth elements, and phosphorus. These elements generate heat through radioactive decay. Park's analysis of Grail's tidal deformation data confirmed that the near-side mantle remains warmer by an estimated 100 to 200 degrees Celsius than the far-side mantle. The warmer interior allows the near side to deform more easily under Earth's gravitational influence, while the cooler far-side mantle retains greater rigidity. This asymmetry helps explain why the Moon looks the way it does. The abundance of radioactive elements on the near side fueled extensive volcanic eruptions between 3.9 and 1.2 billion years ago, filling large impact basins with dark basaltic lava. These volcanic plains dominate the lunar face visible from Earth. In contrast, the far side, with its colder and stiffer interior, never experienced the same degree of volcanism, leaving it covered in rugged highlands and ancient craters. The tidal flexing data, therefore, tie directly into the broader history of lunar evolution, showing how internal composition differences produced the stark hemispherical dichotomy seen today. By understanding the Moon's tidal response, scientists gain insights into how small rocky bodies with uneven compositions evolve over billions of years. The Moon's behavior can be compared with that of other tidally influenced worlds, such as Jupiter's moon Io, which undergoes extreme volcanic activity due to tidal heating, or Saturn's moon Enceladus, whose subsurface ocean is sustained by tidal flexing. Although the Moon's activity is far more subdued, its near-side-far-side asymmetry offers a valuable intermediate case for studying how tidal forces interact with internal structure. The confirmation of lunar flexing also has practical significance for future exploration. Knowing how the Moon responds to Earth's gravitational pull helps refine gravitational models used in navigation and orbit planning for missions, such as NASA's Artemis program. It also highlights areas of scientific interest for future landers and rovers, particularly regions on the near side, where residual heat and radioactive concentrations remain higher. But wait, there's more. Other lunar secrets still under investigation. For much of the 20th century, the Moon was regarded as a fossilized remnant of the early solar system, whose most active days had ended billions of years ago. However, more recent missions and analyses have upended this view, showing that the Moon is not the dead body it was once believed to be. Instead, its interior still bears subtle signs of activity, and its surface preserves clues that continue to reshape our understanding of planetary evolution. One of the most persistent mysteries involves the occurrence of deep moonquakes. Detected by seismometers placed on the lunar surface during NASA's Apollo missions, these quakes occur hundreds of kilometers beneath the crust, far deeper than typical tectonic earthquakes on Earth. Unlike the shallow moonquakes, which are often tied to tidal stresses from Earth's gravitational pull, deep moonquakes recur in clusters and are thought to be linked to localized zones of partial melting within the mantle. This suggests that the Moon's interior retains residual heat, especially beneath regions enriched in radioactive elements. Thermal anomalies in these areas may have kept small pockets of mantle material in a softened or partially molten state for billions of years. Such findings challenge earlier assumptions that the Moon had cooled into a completely solid and inactive body soon after its formation around 4.5 billion years ago. Instead, they indicate that geologic activity, albeit at a muted level, may still persist today. The discovery of relatively recent volcanic activity has been another surprise. In December 2020, China's Chang'e 5 mission successfully returned lunar samples from Oceanus Procellarum, marking the first lunar sample return since the Soviet Lunar 24 mission in 1976. Radiometric dating of these basalts revealed that they crystallized as recently as 120 million years ago, during the Cretaceous period on Earth, when dinosaurs were thriving. This date is staggeringly young compared to the widely held view that lunar volcanism ceased about 1 billion years ago. The presence of such young volcanic deposits implies that the Moon retained sufficient heat to generate magma long after most scientists thought it had gone cold. Researchers propose that high concentrations of heat-producing elements combined with localized mantle anomalies allowed volcanism to persist in isolated regions. If confirmed by further missions, this finding would change everything. It would make our Moon one of the most enduringly active small bodies in the solar system. Central to understanding both deep moonquakes and late-stage volcanism is the distribution of KREEP. You see, potassium, rare earth elements, and phosphorus are byproducts of the final stages of magma ocean crystallization, which occurred roughly 4.43 billion years ago. Because they are incompatible with early crystallizing minerals, they became concentrated in the last pockets of molten material. The fact that creep is concentrated almost entirely on the Moon's near side raises fundamental questions about the events that shaped lunar formation. Some models suggest that Earth's gravity may have influenced the distribution of heat-producing materials, while others propose that a colossal impact during the Moon's early history created an asymmetric mantle. Regardless of the cause, this uneven spread of creep has had long-lasting consequences, fueling volcanism, prolonging mantle heating, and shaping the Moon's geologic dichotomy. The Moon's unusual composition also makes it an attractive site for resource exploration. The near side's volcanic plains contain rich deposits of titanium and iron, which could be used in future colonization efforts on the lunar surface. Silicon, another essential material for electronics and infrastructure, is found in abundance in the lunar regolith. Beyond these familiar resources, the Moon offers helium-3, a rare isotope deposited by the solar wind. Because helium-3 is scarce on Earth, but potentially useful as a fuel for future nuclear fusion reactors, its presence on the Moon has drawn attention as a long-term energy source. However, helium-3 is not evenly distributed. Concentrations are higher in the regolith of the lunar highlands than in mere basalts. Mapping and quantifying these deposits through orbital missions and landers will be crucial for planning sustainable lunar settlements. The implications of these discoveries extend well beyond the Moon itself. By providing a natural laboratory for studying the effects of asymmetric thermal evolution, the Moon helps refine theories of planetary development. For instance, Mars exhibits hemispheric differences in geology, with its northern lowlands and southern highlands resembling a planetary-scale dichotomy. Similarly, Mercury's interior dynamics may have been influenced by uneven heat distribution in its early history. Even exoplanets orbiting close to their stars might experience tidal heating and asymmetric cooling processes similar to those now suspected on the Moon. Geophysical mapping missions have played a crucial role in uncovering these hidden processes. NASA's Grail mission created the most detailed gravitational maps of the Moon to date, showing density variations beneath the surface that correlate with volcanic features and tectonic structures. These maps not only help scientists probe the Moon's interior, but also have practical applications in improving navigation and landing precision. Positioning, navigation, and timing, or PNT systems, which depend on highly accurate models of gravitational fields, are vital for ensuring that future spacecraft can land safely within a few meters of their targets. For rovers, accurate terrain models are equally important for planning routes that balance scientific objectives with safety considerations. From a broader perspective, the Moon's lingering geological activity demonstrates that small bodies can remain dynamic for far longer than once believed. The recognition of deep-seated thermal anomalies and late-stage volcanism fundamentally alters the narrative of the Moon as a fossil planet. Instead, it is now seen as a complex body with a layered history that spans from its violent birth in a giant impact to subtle internal processes persisting into the recent geological past. Each discovery narrows the gap in our knowledge of how planetary interiors evolve, cool, and sometimes retain activity despite limited size and lack of atmospheres. But wait, there's more. Artemis and the future of the Moon. Officially announced in 2017 and accelerated under the first Trump administration in 2019, NASA's Artemis program represents the most ambitious attempt since Apollo to establish a lasting human presence on the Moon. While Apollo was about planting flags and proving capabilities during the Cold War, Artemis is about infrastructure, science, and preparation for deeper space exploration. Its long-term vision is to build the foundation for lunar colonization by the 2030s, with missions involving international partners such as ESA, JAXA, and the Canadian Space Agency, as well as private industry through contracts like SpaceX's Starship lunar lander and Blue Origin's Blue Moon system. The The discoveries from missions like Grail and Chang'e 5 are directly shaping how Artemis is being designed. Gravitational mapping, for instance, improves the precision of landing systems, allowing spacecraft to target scientifically rich or resource-heavy areas, such as the lunar South Pole, where Artemis 3 aims to land astronauts as early as 2026. These regions are thought to contain water ice in permanently shadowed craters. This is an essential resource not only for sustaining human life, but also for producing rocket fuel through electrolysis of hydrogen and oxygen. Accurate knowledge of the Moon's internal asymmetry and crustal density variations also informs seismic monitoring, ensuring habitats and infrastructure are placed in geologically stable zones less prone to moonquakes. The findings about residual heat and localized mantle activity influence where colonization efforts may concentrate. Areas enriched in KREEP, elements and thorium, concentrated on the near side, point to regions with distinct thermal histories, where volcanic plains provide smoother landing zones and easier access to resources like titanium and iron. Understanding the Moon's geologic two-faced nature helps mission planners balance scientific priorities with practical needs for construction materials, shielding, and energy production. The possibility of harnessing helium-3, a rare isotope deposited in lunar regolith, is also being taken more seriously, as it could serve as a future fuel for fusion reactors. Thus, the Moon is not just a future colony, but also an energy hub for Earth and beyond. Artemis is also setting the stage for technologies that will enable permanent habitation. Modular bases, such as the proposed Artemis Base Camp, will include habitats designed to withstand lunar radiation, regolith storms, and extreme temperature fluctuations ranging from 120 degrees Celsius in sunlight to minus 170 degrees Celsius in shadow. Power systems, including solar farms and small nuclear reactors like NASA's Kilo Power, are being planned with resource mapping in mind, ensuring settlements are placed in zones with both sunlight exposure and access to subsurface volatiles. Lessons from Grail and other geophysical surveys are crucial for locating structurally sound regolith layers suitable for tunneling or 3D printing habitats directly from local materials. Every insight about lunar flexing, residual volcanism, or crustal asymmetry contributes to a blueprint for how small bodies retain heat, sustain activity, and evolve over billions of years. These models are directly applicable to Mars's volcanic past, Mercury's crustal dichotomy, and the thermal dynamics of tidally locked exoplanets. The Moon is thus a stepping stone, guiding humanity into a broader cosmic understanding. Well, that's it for now. Thanks for watching. Did you like this video? If you did, please consider liking, dropping a comment, and hitting the subscribe button so that you don't miss out on our new uploads. Also, don't miss this video you see on your screen right now. It's truly unbelievable.